Hi everyone, welcome back. So in this video, we're going to look at how we can calculate the electric force that a charge will experience when placed in a field, and also the electric force that one charge will exert on another charge, because that's what happens when you put a charge in a field. Okay, one charge exerts the field, the charge you place in the field is then going to experience a force because of that. Okay, so what you can say is that one charge is exerting a force on the other one, and that's what we're here to calculate in this set of notes. Okay, so there's your dot point. We're going to be using this equation here. Let's get to it. So you got to think about what the electric field strength means. Okay, well, the electric field strength is a force per unit charge. Okay, so the relationship between the field and the force is this. Okay, so if you put a charge inside an electric field, the force that it would experience is sort of proportional to how much charge there is. Okay, so rearranging that little expression there gives you F equals QE. We saw that in one of the previous videos. However, we know that the electric field strength can be written as this, okay, where this capital Q is the charge that is exerting the field, okay, and R is the distance between that charge exerting the field and that point in space around the field where your second charge is going to be placed. Okay, so if you place a charge with a size of little q in that spot in the field, then you can just replace this E here with this equation, KQ on R squared. That's what we've done here. And then you just multiply the size of that test charge with the size of the charge exerting the field, and you get Q times Q in the numerator. Okay, now that can get a bit confusing if you're trying to explain it in words. So typically we just say Q1 and Q2 rather than big Q and little q. Okay, and that's the equation that you see here. Okay, so this is the electric force between 2 point charges. Okay, just like you can have a mass exerting a force on another mass via the gravitational field, you can have a charge exerting a force on another charge via the electric field. Okay, and that's your equation. Okay, so commit that to memory. It's very, very similar to the gravitational force equation, which is big G times M1 times M2 on R squared. And again, like I said before, you're going to see a lot of parallels between electric field and gravitational field. All right, so force measured in newtons, pretty straightforward. Q1 and Q2 are the charges that are exerting forces on each other, and R is the distance between them in meters. Okay, the direction of the force, well, you've just got to remember that if the two charges are opposite signs, so one positive, one negative, then you say the force is attractive. So one object or one charge gets attracted to the other one. If the charges are the same sign, so both positive or both negative, then the force is away. Okay, so they're getting repelled. Okay, so you just got to remember that. There you go. That's your equation. Okay, nothing to it. Now, again, just I know it doesn't really need to be said, but we'll say it anyway. Okay, Newton's third law. Okay, for every force, there is an equal and opposite force in the other direction. So that means if charge 1 exerts a force on charge 2 via the electric field, then charge 2 is also exerting the same magnitude force on charge 1, just in the opposite direction. Okay, so it doesn't actually make any difference whether you say that charge 1 is making the field and charge 2 is being placed in the field, or charge 2 is making the field and charge 1 is being placed in the field. Makes no difference. Okay, the two are equivalent in terms of the forces that the charges would feel. Okay, the size of the field, the magnitude of the electric field might be different in those two cases, but the force that each one would experience is the same, no matter which way you think about it. Okay, so there you go. All right, let's do a question. So see how we can apply this equation. So we've got a 2 millicoulomb charge. So that's 2 times 10 to the negative 3. is placed in an electric field with strength of 1 times 10 to the 4 newtons per coulomb. What is the magnitude of the force this charge would experience? Well, you've just got to remember that electric force is equal to charge times electric field. Okay, if you place a charge in an electric field, the force that that charge would experience is just the product of those two values. So we've got 2 times 10 to the 3, negative 3, times the field, which is 1 times 10 to the 4. Okay, you don't even need a calculator to do this. 2 times 1 is 2. 10 to the negative 3 times 10 to the 4 is 10 to the 1, which is just 10. So you've got 2 times 10, which is 20 newtons. Okay, it's good to be able to sort of work things out like that. Okay, you don't necessarily always want to type something on a calculator. Obviously, if you're not comfortable doing things in your head, then use a calculator. Okay, that goes without saying. But if you want to save yourself a bit of time in an exam or something like that, try and do some basic calculations like that in your head. Okay, because typing 2 times 10 to the negative 3 times 1 times 10 to the 4 in a calculator, it's going to be more time consuming than just doing that kind of thing in your head. Okay, but like I said, if you're not comfortable doing that, then of course type it on a calculator. Okay, only if you're comfortable, do it in your head. All right, so there you go. Okay, force is charge times field. Okay, so if you've been given a charge and you've been given the field strength that the charge has been placed in, then you just multiply those two things together. Okay, otherwise, the other type of question you can get is something like this, where you've got two charges and you're trying to work out the force between the two charges. Okay, so we've got a simplified model of hydrogen atom represents an electron orbiting, and orbiting is in quotation marks because it's not really orbiting. It's like existing. We're not going to get into it. Okay, just pretend it's like a planet going around the sun. Okay, so model of the hydrogen atom represents an electron orbiting a proton, like a planet orbits the sun. Okay. If the average distance between the two particles is 5.3 times 10 to the negative 12 meters, which 10 to the negative 12 is picometers, okay, calculate the average force between the proton and electron. Okay, and we've got to use E, which is the charge of electron and proton, equal to 1.6 times 10 to the negative 19. Okay, so we've got two charges, we've got a distance between them, you want to work out the force. Okay, so that just goes straight to the formula. Electric force is equal to K times Q1 times Q2 over R squared. K, 8.9 times 10 to the 9. Q1 and Q2, well, they're both 1.6 times 10 to the negative 19. Okay, the charge of an electron is the same as the charge of a proton. Okay, so it's 1.6 times 10 to the negative 19 times 1.6 times 10 to the negative 19. You just square it. Okay, don't bother typing it in twice. 1.6 times 10 to the negative 19 squared over the distance between them, 5.3 times 10 to the negative 12 squared. Okay, when you're typing on a calculator, remember to put brackets around your numbers just to avoid any silly mistakes when you square things. If you don't put brackets around that, the only thing you'll be squaring is the times 10 to the power of whatever. All right, putting that on your calculator will yield an answer of around 8.2 times 10 to the negative 6 newtons. Okay, there you go. Okay, just straightforward using the equation, nothing to it. All right, so that's it for this video. We now know how to calculate the field strength from a point charge, and we know how to calculate the electric force between 2 point charges separated by some distance. Okay, and they're just very straightforward calculations. So there you go, that's it for this video. I'll see you next time.